Okay, moving on again. Can you imagine I have to say this for 1.5 hours? Oh. Yeah, man. Don't worry, I'm trained, I should be fine. Yeah, I don't think anyone of you is worrying about that. Yeah. Okay, next. Right. One block pushes another, right? These are the forces you feel. Considering M1, right? These are the forces you feel, and M1 will have a normal action force N1 acting on it. P, what's P? P is the force that block M2 acts on M1, right? So by Newton's third law, P and P prime, right, are the Newton's third law pair forces. So on block 2, there will be a force of P is a force of M1 on M2. These are the forces that you find on them. Okay? So if I consider them together, which is a good technique, right? Always try to solve for the common acceleration. Unless block 2 is eating into block 1, that's a different situation, right? But generally, we do not have that. Considering forces on M2, then you can find the P very quickly. So finding P is a very common physics question, even in H2. Okay. Method 2 is a bit too long, so I think I did not give it, right? Method 2 is a bit too clumsy, so use method 1, my recommendation. Find the combined acceleration, find the force on P2, that's it, done. Right? You can see method 2 is highly convoluted and painful. The mathematics is very lousy here. Right? There is a quicker way for method 2. I've looked at it, but I've been a bit lazy to change the slide. Okay, so just use method 1. Okay? Good. Moving on. This one. This is the one. This is the one. Don't look at answer. Don't look at answer. I want you to try it now. Right? Oh no. Read the question and draw the free body diagram on PET. Draw the free body diagram on the chair. Right, and draw another one for PET and the chair. Can you try it now? I'll give you 1 minute. This would be classified as a tough H2 question, but it's a standard question in Olympiad. Okay. Right, so what do you see? You pull, and the spring scale reads 250 newtons. This means that the tension in the rope is 250 newtons. We make an assumption that the pulley has no friction, so the tension here is also 250 newtons. Okay. The PET's true weight, PET is pretty light, probably a child. It's a child, 32 kg more or less, 320 newton. The weight is about 16. The chair is about 16 kg, 160 newton. So how do you draw the free body diagram? Well, let's look at PET. So PET, put the weight of PET, and when PET pulls on the rope, do not forget that there's an upward tension. So this is the first answer. Is that the end? Is that the end? No, because when PET is sitting on the chair, there is also a force of the chair on PET, given by this N. Okay? Forces on the chair. The chair is being hung by a rope, so there must be upward tension on the rope. The chair itself has a weight, so 160 newtons. So these two forces are obviously there. Now, Newton's third law says that if the chair is acting a force on PET must exert also a downward force on the chair. Okay? So this question challenges a lot of H2 students because they either not consider tension, or they either forget N, or they write this N but they forget this N, you know. So on first try it's actually pretty difficult. But there is a quick method for this, and it's by combining all the upward forces and downward forces together, you realize that you can remove N altogether, don't need to solve for it. So the upward forces on these two objects combined together is 250 times plus 250, which is 500. The downward forces is 480. So naturally, naturally there will be upward acceleration on this combined mass. Right? Ta-da. So there will be an upward acceleration of 0.408 meters per second. All right, 10. Does this surprise you? This is actually a real life mechanism, right? The photographers from National Geographic, they climb big trees to look at monkeys and birds. They use this same pulley system, right? They hook a rope over the tree, they hook a pulley there, then they pull themselves out. Right? This is the same system. Okay? Okay. Any questions on this? Should be relatively simple. The next part asks you to find n. Right? So now you consider forces on pad itself. Right? You will have 250. Right? Just consider this part. Forget all the other pictures. Just consider this part. Upper force is 250. Downward force is 320. And can be considered to be 83.3 newtons. Right? Any questions? Yes. Questions? (320) divided by G is the mass. 320 divided by G is the mass. Yes, question? There's some discussion there. Question? No? All right, as I promised you, there will be lots of questions on bananas and monkeys. Sorry, on monkeys actually. What will happen? Don't look at answer. I want you to try this. Okay. As the monkey climbs, what happens to the banana? So as the monkey and the banana are both the same mass. So when the monkey climbs, he exerts a tension on the rope. Agree? Which is the upward force on the monkey. The T must be bigger than its own mass for him to climb. Agree? Pull, tension must be bigger than my weight for me to climb up. But when T increases, do you agree that on the side of the banana, the T also increases? So both the monkey and the banana have the same upward force acting on them. And they have the same mass, so the acceleration is the same. So as the monkey accelerates, the banana accelerates. Correct or not? So the monkey realizes that I cannot climb up, I cannot get a banana. Oh no. Right, so the question is, as he moves up, the banana moves up, right? The distance stays the same because they have the same speed and acceleration. Right? They are initially a distance away, so let's say 10 meters. It climbs up. Both velocities are the same, right? So you can't actually get it. If they hold on to the rope, the tension equals its weight. It's no longer accelerating. The banana is not accelerating. The monkey is not accelerating. The banana is also not accelerating. Still cannot reach the banana. He lets go of the rope. Also cannot work. Right? So what does this story tell you? If you are a monkey, you will never reach a banana. No, so there are other ways. So if I'm the monkey, I'll just let go of the rope, let the banana fall to the ground. Right? So yeah, do not hang on to the rope. Right? Maybe letting go is the best. Oh, so cheap. Okay, moving on. Friction. Friction. There are two parts. Okay, there is this one you will not know. Okay, in your H2 you will not know. There's a static friction and there's a kinetic friction. Okay, as I put my wallet on my face, right, and I start to pull it down, right, there's an increased friction of my face on the wallet. Right? Yes, those at home, you did not get to see this scene, which is quite funny. So, as this happens, right, the friction rises along the curve until the moment the wallet starts to move. The moment it starts to move, actually, your kinetic friction is at a lower value than the maximum static friction. Which explains why when you try to push something heavy along the ground, the moment it starts to move, it feels a little bit easier. Have you had this experience before? Right? Once it starts to slip, it slips a lot more. Okay? Which also means it gets harder to stop. Right? What actually causes friction is all these microscopic surfaces. They are not perfect. So this also explains why you feel very little friction on glass and ice and a lot of friction on sandpaper. If I put sandpaper on my face, yeah, not gonna push it. Right, so these are the laws of friction. Static friction given by friction subscript S, mu, coefficient mu, subscript S is the coefficient of friction in static. N is a normal reaction force, which means this, slightly not intuitive. Look at this physics textbook on the table. What is this N? The N is the weight, correct? So if I have this, the whole book on the table, and I try to pull it, the friction is the same when it's fully on the table and 3/4 on the table. The friction is the same. Surprise? No, oh, very good. Not surprised, very good. That means you have a good. If it's halfway, also can. If it's left 1/4 on the table, got friction. No, of course, because the N will be 0 already. You will fall off the table. So, those at home cannot see this. So if you pull, then the friction stays the same actually throughout. Okay, of course, we are making the assumption that the surface of the table, the coefficient of friction is more or less the same throughout. Moving on, coefficient of friction is generally around 0.05 to 1.5. Wait, isn't this interesting? The coefficient of friction, it can be up to 1.5. Interesting, huh? Interesting, huh? When I first learned about this, my first gut instinct is usually this kind of coefficient always go up to 1 only. But there are actually surfaces where it can go up to 1.5. Oh, interesting. Okay, you can go and find out what material that is. Let's look at this paradox. A horse pulling a sled along a level, snow-covered road, causing the sled to accelerate. Newton's third law states that the sled exerts an equal and opposite force on the horse. In this view, how can it accelerate? Right? Whether the horse pulls on the sled pulls back on the horse. So why is the horse moving? It's because I confuse you with words now. I confuse you because there is when the horse is moving, you must consider the force of the ground on the horse. Right? Force of the when I walk, why am I moving forward? It's because when I dig in, there's a force of the ground on me forward. I exert a force on the ground backwards. The ground gives me a force. So you should not be considering the force between the horse and the sled. Right? You should consider the force of the ground on the sled and the horse. So it's not actually a paradox, it's just a misdirection, right? So as I say, look here when the magic is happening. Okay? It happens quite often. Okay, so all you care about is whether the force on the horse, by the ground on the horse, is bigger than the force of friction on the sled. That's all you care about. The action reaction pair forces you don't really care. Okay. Example, yes, question 11. I don't think I can finish all 14 today. I will probably stop with some. Okay, then next week when you come back, I'll give you the rest of part 2 of the notes. There's another 14 questions to come. 2 kg block placed on top of 5 kg block. The free friction between 2 blocks, 5 kg block is 0.02 and off surfaces. Calculate the force needed to pull both blocks with an acceleration of 3.00 meters per second. Okay, state the minimum coefficient of friction between the blocks such that the upper block does not slip under the acceleration. So this is a simple example. I'm not going to waste too much time here. If you consider both of them moving together, the total mass is 7 kg. You want an acceleration of 3, and you also consider then the friction. Kinetic friction, you consider kinetic friction because it's moving. So the vertical direction the sum of forces must be 0. So you can actually find the value of N to be 68.6 Newton. So you must find N. After finding N, you can know that the kinetic friction is this value by using the formula. Thereafter, you can find the horizontal force required, right? The sum of the horizontal, the net horizontal forces is the forward force F minus the friction, kinetic friction. This will be equals to the total masses times the acceleration required. Sub in the values required. This is 7, this is 3. The friction is 13.7, so the horizontal force you might exert is 34.7 newtons. This is pretty straightforward. If you now consider the 2 kg mass alone, you have to find what's the coefficient of friction required between the 2 kg and the 5 kg block. You know that the normal reaction force between them is actually 19.6. That's easy from the mass of the 2 kg block. The horizontal forces on the block must be equal to the friction, static friction, because now the block is not moving, it's a static friction. So static friction must be equal to MA, 2 times 3 equals to 6. There you go. Easy peasy, you have the static friction coefficient. And you realize that the static coefficient of static friction is smaller than the coefficient of kinetic friction. Okay. Questions? No. Moving on. Right. This page just nice for y'all? Okay, good. Wow, y'all good. Wait till you see the later question. Okay, so moving on. Block of M1 placed on inclined plane with a slope of alpha. With a block hanging over it, mass 2, applying a small frictionless pulley. Find the mass M2 for which block moves at a constant speed 1 second motion. Oh, interesting. Let's consider forces. So force on M1 will be M1G, Newton, normal reaction force, and T. These will be the 3 forces acting on it. Right? I want you to see something. It is moving at constant speed. Do you agree? Constant speed. So the forces should pass through the same point. Huh? Should pass through the CG. Okay. Interesting. So here, if you see another force, so this N should actually, in fact, be slightly back. Right? N should actually be slightly back. So that because T and Fk will give you a force that acts slightly lower in this direction. Right? This should be here. Interesting, eh? Anyway, that one is for another time of discussion. That is too minor. Let's not talk about that. Sorry. Let's move on. Let's focus on the issue at hand, which is to solve for which one? What are you solving for? I don't have the question paper. You all took the last question paper. What is this question solving? Okay, then fine, whatever. We are solving for the coefficient of friction, right? So find the mass M2, sorry. Okay, so there you go. Let's consider a force on M2. If you have constant speed, there's no acceleration, so T equals mg. Okay. T will be equal on both sides. So T minus m1g sine alpha minus coefficient of friction, the friction is equal to 0. Not a problem. T minus mg sine alpha equals to minus friction equals to 0. So an easy way to remember the component of weight that acts along the slope is that the block will slide. Slide starts with S, sine is an S, so mg sine alpha. Okay, that's a way to remember it. So coefficient of friction is UK, right? Times the normal reaction force. This easily gives you mg cosine alpha. Hence, you substitute this in, you get m2g, tension becomes m2g. Bring everything to the right hand side, you get this whole chunk. You divide by g. Throughout, you get m1 sine alpha plus uk cosine alpha. There you go, that is your mass 2. Okay? Part B. Oops. Part B, they ask for M2 for which the block moves down the plane at constant speed once it's at the motion. Okay. Find the mass M2 for which block one moves up the plane at constant speed once it's at the motion. Isn't A and B the same? Oh, moves down. Okay, part B, you want it to move down the plane. Ooh. If it moves down the plane, what's the direction of friction? Opposite. So the other way. So basically, it's repeating the whole chunk, but now you see that instead of negative, it's positive, right? So it's not that hard. You rearrange, you get the same answer, just that the sign has changed. Easy peasy. Yeah? Part C, what's part C about? I really don't have the question paper anymore, right? Because you're to the last one. I should have one by right. Oh, wait. Part C, for what range of values of M2 can the block be to remain at rest if released at rest? Right, so you want to have a range of values. So if right, M2, right, so in part A and B, you have these two masses, right? So obviously it should be between these two masses now. The intuition tells you that. Okay. The math seems difficult, but the intuition tells you it should be in between because anything smaller, the friction should be able to take over. Anything larger, you will overcome the friction, right? So anything too small, right? If it's too heavy, you'll pull the block. If it's too heavy, you'll pull the block one up. If it's too light, block one will pull it down. So you want something in between that range, which is as it is. Okay. Right. Maybe this is a good time to pause. Yes. All right. It probably is a good time to pause. So we will continue next lesson.